How can structural engineering optimize materials for strength? Imagine building a bridge that uses half the material but is twice as strong. That's the power of how structural engineering can make materials work smarter, not harder. When engineers design massive structures like skyscrapers or long-span bridges, they need to find the best way to use materials so they can handle enormous forces without wasting resources. This process is all about making structures safer, lighter, and more cost-effective. One of the main ways engineers do this is through topology optimization. Think of it as a digital sculptor that shapes the material inside a design space. It removes unnecessary material from areas that don't experience much stress and keeps it where the forces are strongest. For example, when designing record-breaking bridges, this method helps create lightweight yet sturdy structures by only using material where it's needed most. Size optimization is another key technique. Engineers adjust the thickness and dimensions of beams, shells, or columns to maximize strength without adding extra weight. For instance, in constructing large buildings, varying the thickness of load-bearing walls or beams ensures they are reinforced enough to handle the weight but don't waste material. This saves money and reduces construction time. Shape optimization involves changing the form of structural elements. Curves, angles, and contours are fine-tuned to distribute loads evenly and reduce stress concentrations. Tall skyscrapers often use this method to improve stability and aesthetic appeal. For example, a building's curved facade can help resist wind forces better than flat surfaces. Surface patterning techniques like adding grooves or ripples to thin materials also boost strength without extra weight. Think of how corrugated cardboard is stronger than flat sheets. This idea is used in aerospace and automotive industries, and in architectural elements that need to be both lightweight and strong. Using computer simulations, engineers can design components with variable thicknesses. Areas with high stress get thicker material, while less stressed zones are thinner. Internal lattice structures with graded density are also created to maximize stiffness while keeping weight low. These advanced designs have helped build some of the most impressive architectural wonders. Modern tools like artificial intelligence and complex algorithms help engineers explore countless design options quickly. These methods find solutions that are often impossible to imagine manually. For example, they can create innovative structures that use less material but are just as strong or even stronger. Choosing the right structural system is also vital. Engineers select beams, trusses, or shells based on the specific loads and environmental conditions. This ensures the structure is strong enough while using the least amount of material. Finally, sustainability plays a role. Engineers now focus on eco-friendly materials and designs that reduce energy use and environmental impact. This approach makes sure that structures are not only strong but also environmentally responsible. All these techniques come together in the work of architectural and engineering giants, allowing them to build colossal creations and natural wonders that push the limits of what materials can do. By carefully distributing materials and shaping structures, engineers turn ideas into durable, resource-efficient landmarks that stand the test of time.